I want to talk about recursive CTEs. Let's take a look. Well, common table expressions, also called CTEs, are extremely useful. And they're extremely useful for improving the readability of our code. There are some other marginal uses of them. For example, if you needed to do an insertion of a record that had multiple parts, so you had to insert across multiple tables, you can use a CTE to do insertions as the subclauses. Since that's an optimization barrier, it'll actually do the insertion. You can have those return some primary key row, and then you can use that. So if you had one table, and in order to insert into this one table, you have to insert into these two tables, and they're foreign key relationships, you could just as easily say, okay, do that in a CTE, do the insert in backwards order from the most granular to the least granular, return the ID, and then in the last query say, insert into blah, 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 select the ID from this query and select the ID from that query. And so, marginal use, but kind of useful. They're great for readability, and they're great for solving a problem that historically has been very tricky to do in SQL. Here's the nature of a problem. We have a hierarchy of unknown depth. And in this case, this represents employees and their managers. And by unknown depth, we mean that there's a boss, somebody who has no manager. There's a null here representing them. But there could be one layer of middle management. There could be 3 layers of middle management. On one part of the company, it could be very flat. On the other part of the company, it might not be as flat. And we might very well want to know questions like, how many total people report to so-and-so? What is the total size of such and such organization? Now, historically in SQL, this was not possible to do. Historically in SQL, if we wanted to answer this query, we could use self-joins in order to do this to a fixed depth. So what we could do is we could say select star from employees as E1, and then we could inner join this against employees as E2, and then inner join this again as employees on E3 and link these joins up, and we get a 3-step, one manager to the subordinate, to the subordinate subordinate. But we couldn't do an arbitrary depth hierarchy. So we'd either have to do this in our application layer in our software programming, or we'd have to use some contortions like Joe Chelko's nested sets, where we use some integer tricks, but those have some severe limitations to them. In modern SQL, we have the ability to do a common table expression, and for that common table expression to refer to itself. And like any recursive approach, this is no different. The formulation of this approach is in terms of some base case and some inductive step. So this query sets up its base case. Select the employee whose manager is null. That's the boss of the company. Then, in the inductive step, select each employee where that employee's manager is, or rather, I should just put that the other way. Select from the recurrence that we had, join it against the employees. We could do this in both ways. So maybe I'll do it. I'll do this the other way around. Maybe we'll make this the from, and we'll in and join the recurrence. So like that. And so here we'll select the. Actually, I kind of like it. I kind of like the way I did it the first way. In any case, what we can do is we can say, okay, go into that recurrence, join what we had selected, maybe the one boss, join that against all of the employees, and then find the places where that boss happens to be somebody's immediate boss. And then repeat it again, and then repeat it again, and repeat it again. And when we construct this, we actually get the full hierarchy of the company, everybody who reports to everybody else, and we can even compute what that hierarchy is. This person, F, reports to A through C, and this is the full hierarchy to them. And of course, we can do this in a couple of different ways. Maybe another nice way to do this would be to put the employee name there, so that, and then to make this the hierarchy with your name. So you get the full path to the person. So F reports to A via C. We can do this in one query without ever hitting the application layer, which is great because we don't have to transmit data over the network. We don't have to have a for loop. We don't have a programming language. We can do this all in just one SQL statement. But there's something about this SQL statement that I don't like. Can you spot what makes this query not only bad, but potentially extraordinarily problematic, especially if we don't necessarily control very closely the input of the data, and we might even control the infrastructure where this database is working on, and we're worried that somebody might blow up our database. I'll give you a hint. What happens, and I'm not going to run this, but what happens if this is a very weird company where people are matrixed in and out? So the reporting lines are not quite as acyclical as you might expect. For some reason, so-and-so reports to so-and-so, and then there's maybe a managerial relationship where they're matrixed here, and somehow a cycle has been introduced. So, in practicality, it's not the case that my boss's boss's boss wraps back around to me, and so I'm my own boss. Probably not, but it may be the case where sometimes there's some gridlock in the organization because one person is waiting for this person, who's waiting for this person, who's waiting for this person, who's waiting for this person, and we got tied up. And that might not be that unusual in practice. Whatever the case may be, these kind of cycles do appear in real data. This might be even a data error. What's going to happen to my query? Does that give you a hint? If you said that not only will my query be wrong, but it will actually be operationally problematic, you're wrong. Because my query will not be wrong. My query won't even finish running. You're right if you said just that it's operationally problematic. What's going to happen if I run the recursive CTE on this data with this cycle is Postgres is going to go and create the data set, and then it's going to see the cycle, and it's going to chase that down again, and it's going to chase that down again, and it's chase that down again. My query will never return, and my database will continue to allocate memory until, honest to goodness, the reason I won't run this is my computer will seize up, and I'll have to reboot it. And I can tell you that because in preparation for this mistake, that happened to me 3 times. So the problem with these recursive CTEs, especially if you don't guard for cycles, is a cycle can be extraordinarily problematic to the point where it can actually bring down the SQL server. Now, of course, there are mechanisms that you can use if there's a multi-user server to be a little bit more careful about that. But you can imagine that especially if you're doing this for your own analytical purposes, even a really long-running query that kind of times out is bad news enough, even if it hasn't taken down the database. The answer to how we want to improve this query is to make sure that we deal with cycles. And the good news is SQL has cycle detection. Postgres specifically has cycle detection built into the syntax for this. All we have to do is set up a cycle by collecting information from the manager. Set a new column called isCycle and use that path for the manager in order to identify this. And even though we still have a cycle here, by annotating the query that we're doing with these additional rows, with additional columns, you can see the isCycle column and this path column. Postgres will run until that isCycle column is true, and then it won't continue running past that. And you can see I got the path for free. I didn't have to construct that myself. Now this is a little bit clumsier because you can see that I got this as tuples of one item. So this is like a tuple of one item where that item is null. And I'll have to do some unpacking. I'll have to do some manipulation to get this to be exactly the same. Really nice formulation with just an array of each of the managers. But I didn't have to do any work to create this extra column. So that has some value. Just have to do a little bit of work to make it useful. In general, anytime you do a recursive CTE, you must consider, are cycles logically impossible as a consequence of something that's happening in the data modeling or the data ingestion? Or am I correctly accounting for cycles? Because you definitely don't want it to be the case where you say, well, they're logically impossible because that would never happen. And I looked at my data and it doesn't happen in my data, and then somebody inserts this row. Note that some kinds of checks and constraints are easy to express in SQL. A cycle constraint is not easy to express in SQL via just the constraint mechanism, in part because the constraint mechanism, like everything else in SQL, operates on a tuple. So the constraint mechanism can look at all the fields of the tuple, but it can't look at other tuples. The only way for you to check to see if you created a cycle here would be to use a trigger on insertion to then do a query of the whole database and to see if you have cycles there. And that might be problematic because that could be very expensive in an insert-heavy circumstance. And so maybe you do this on select. You identify the cycle and then you terminate. Whatever the case may be, probably it's a good idea to just do this just in case if you're not 100% sure. As with all of these cases, I want to make sure that we have a good understanding of the explanation. So I want to take just a moment to talk about CTEs and recursive CTEs. Oftentimes, we find that we need to model some kind of hierarchy. For example, if you had a website and you wanted to allow people to tag things so they could easily find shirts, well, shirts are part of tops. And button-down shirts are a part of shirts which are a part of tops. But there's also things that fall out of this hierarchy. It's very nice to be able to give them both a ontology that is based on tags and an ontology that's based on hierarchy and to create the intersection of those. These are very easy to do in Postgres because you can create your tags, you can create your join table between the entries you have and the tags you have, and then you can create another table that's the hierarchy of tags. And you can say, if you pick this tag, it implies these other tags, and you let people pick all the tags. So give me all of the button-down shirts or all of the bottoms or all of the long coats. And you can imply from that, okay, button-down shirt goes down to button-down shirts with the 1950s NASA-style pocket. Bottoms goes down to trousers or shorts, and so forth and so on. And you can use the recursive CTE very nicely within a CTE. Bear in mind, this CTE is just one thing that you tack on top of the query to then infer all of the tags, get those tags, and then power those into your normal query. And you can do some pre-caching here if you want. You could materialize this in some fashion. Generally, the use of recursive CTEs are a really nice way to improve your data modeling because some things naturally have a hierarchy or something implies something relationship. And if you can do this in just one CTE clause at the very beginning of your query, no big deal. But you do have to be aware that there could be cycles that appear, and so you should be aware of cycles. When you write CTEs, it's very easy to get confused of the syntax for it. And so when you look at this, I want you to think of a couple of key things. Like any recursive formulation, it is always some base case. What are you starting with? The first part of this is always the first part of the query that launches everything. Remember, it's always about the selects and how you build up those selects that powers how the rest of the query works. And so here, this is the starting point, select where the manager is null. If we wanted to select for a specific manager, we might say select where manager equals D. Then a union all. Why? We definitely don't want to eliminate duplicates, but although in this case it's not going to make much of a difference because this path should be unique, or at least a tuple containing all of these should be unique. And so I don't know. I mean, I feel like I'm going to do a union all here because I don't want to leave it to chance, especially if we add or remove columns. One thing to keep in mind is a good SQL query should continue to work even when people add extra columns to the result set or when the table has extra columns introduced. There's nothing wrong with select star as long as you think, whenever you write a select star, if they added another column to the table, would this still work correctly? Would distinctness still be upheld? Would ordering still be deterministic? And so forth and so on. In other cases, as long as you've thought of that, you might say, what, I don't feel comfortable with the select star. I'm going to explicitly select the columns because I don't know if maybe as a consequence of a database backup and then restore process, maybe the column ordering has changed, and I don't want to be too reliant on the column ordering or things like that. Well, the other part of this recursive query, like with any recursive formulation, is the inductive step. And the inductive step is always, given some base case, how do I get to the next part? And for a recursive CTE, it almost always looks the same way. You take what the state of what things are, and then you join that against something else to get the next state. And what you're going to think is actually happening behind the scenes is this inductive step is basically just being run over and over and over again until this thing terminates, until that inductive step no longer returns new rows. And so what you're going to do in this inductive step is you're going to typically join or select from the CTE itself, and then join or select from, depending on which order you want to do this in, the actual data itself, and figure out how they link to each other. And so I struggled when I wrote this because I hadn't written a recursive CT in a while. But when I look at it, I say, oh, you know what? Why did this make any trouble for me? This is absolutely obvious. It's always a base case, and it's always an inductive step, and that inductive step is always some sort of operation on the recurrence, or sorry, the recursive state, the CTE itself, and the actual data itself, and that relationship is probably going to be some kind of join. On top of that, I add my cycle, and I'm good to go. And I just think for a second, hold on a second, does this make sense in the case where things are null? If one of these are null, then this would not be equal, so that'll be dropped. So this will be correct because this will select all those null managers. So if this company happens to have multiple bosses, this should be correct and give us all of the bosses. Oh, but note, it only gives us, oh no, gives us all the bosses. Gives us all the bosses right there. So this works. These are the things you need to keep in mind if you want to make sure that you write queries that are not mistaken, that you write queries that work well. Thank you all for joining us, and I'll see you all next time.